Hello everyone, welcome to the lecture series of pattern classification. I am Kundan Kumar, and if you would like to have these lecture slides, you may refer to my GitHub page at this given link. In this lecture, I would be discussing the classifiers, that is the statistical classifier. Then we will discuss the discriminant functions, and also we will discuss the few the density functions, particularly for the Gaussian distribution function and the decision surface. So here this figure shows the functional structure of general statistical pattern classification. So this is the functional structure that need to be understood. Here we have C number of discriminant function which is defined for each individual C classes, and each discriminant function takes the input as the feature vector, where the feature vector having the dimensionality as the D inputs. Then this discriminant function computes the cost for individual class, and then based on this cost it takes some action or it do the classification. So in the subsequent steps it determines that which of the discriminant value is the maximum. That means if we compute the cost, then for these individual discriminant functions, then we will find that which discriminant values is the maximum and categorize the input pattern accordingly. Okay, so this is the general statistical pattern classification system. So what is the discriminant function? The discriminant function is a very useful way of representing a classifier through the discriminant functions. So here we can define C number of discriminant functions for C different classes, and we classify or we assign a feature vector x to class omega I if the discriminant function of ith class is greater than the discriminant function of jth class for all j but not equal to I. So for this classifier we have to consider, that means we have to maximize the discriminant value. So if we consider the minimization, classifier where we need to minimize the conditional risk, then our discriminant function can be defined as the negative of the risk, because the risk factor we need to minimize, and if we have to define a discriminant function that is to be maximized, then definitely we have to take the negative sign over that. So for the classifier that minimize the conditional risk, then we have to define our discriminant function using this expression. And for the classifier that maximizes the error, then for the classifier that minimizes the error, because we have to minimize the error. Okay, so in that case we have to consider the discriminant function as the posterior probability of the class, because we have to maximize the posterior probability of class to minimize the error, and the base and the minimum error is basically the base error that we already have seen. So these functions divide the feature space in C decision regions. So these discriminant functions, it divides the feature space in C decision regions which is separated by decision boundary, and here the C decision regions are R1, R2 and RC. So please note that here the results do not change even if we replace every GIX by a function of GIX if the function is monotonically increasing function. So if whatever the classifier we will design using the discriminant function, and if we apply some function on the discriminant function, our decision rule will not change if the function is monotonically increasing function. So kind of logarithmic function. Logarithmic function is basically a monotonically increasing function. So why we do this? Because if we apply some monotonically function to the discriminant function, it will ease our calculation. That means it lead to significant analytical and computational simplifications. For example, let us consider the minimum error rate classification problem. So here the discriminant function is defined as GIX equal to the posterior probability of the class, ith class. Okay. So using the Bayes rule, we can put this value, and here all the probabilities are in the multiplication and addition, which is difficult to handle this problem. Okay. So here the denominator part will not contribute anything to make the decision. So this denominator part can be omitted. So we have the discriminant function as the likelihood into the prior probability. So here these two terms are in the multiplication. So always addition is better than a multiplication. So we can apply some monotonically function like logarithmic function we can apply on this discriminant function, so that this multiplication term will convert to the addition term. So this is the new discriminant function, okay, which is the summation of the two term, which is the ln of the likelihood plus ln of the prior probability. So in many examples we will see that by applying the logarithmic function to the expression, it will ease our calculation and it will help us to make our decision easier. Now we are going to discuss the decision boundary, and here we will discuss the two category case, which is a special instance of multi-category case. So you have seen that we have defined the discriminant functions for individual classes if we have C class problem. So here we have the two class problem, so we can define the two discriminant functions g1x and g2x. So if we have the two discriminant functions, then how we can make the decision? We have to assign a feature vector x to omega 1 if the discriminant function of class 1 is greater than class 2. Okay. So instead of comparing these two discriminant function, we can make a single discriminant function where we can define the gx equal to g1x minus g2x. And here we can observe that this condition, which is g1 greater than g2, so if it will be satisfied here, that means gx will be greater than 0. So that means this condition can be satisfied with the single discriminant function, and that discriminant function is nothing but our decision boundary. When we will equate this discriminant function, then it will be our decision boundary. So now we can define the decision rule in terms of the decision boundary discriminant function, that we have to decide omega 1 if gx is greater than 0. Otherwise we will decide omega 2. Now let us write a discriminant function for minimum error rate classifier. So just on the previous slide, we have seen that our discriminant function for individual class is the posterior probability in case of minimum error rate classifier. So here we have two class problem. So we can define the posterior probability for class 1 and class 2, and we will take the difference of these two posterior probability, then it will give us the discriminant function, and that discriminant function will define the decision boundary between these two classes. So now we can expand this expression as that this is the posterior probability, and we can write it as the likelihood into prior probability. Okay, and we are just omitting the evidence because it does not contribute anything to make a decision, because the evidence is common for both the classes. So here we can write the posterior probability as the product of the likelihood into and prior probability. So here posterior probability for class 2 will be likelihood of class 2 into the prior probability. Okay. Now to simplify this expression, it is little bit difficult. So now we can think of that we can take that logarithmic. We can take the logarithmic of this discriminant function so that this multiplicative term will come into the addition, and it will be easier to simplify it. So if we'll take the log of the discriminant function, that means we will define a new discriminant function which is the logarithmic of this discriminant function. So it will be ln p of x omega 1 plus ln prior probability, okay, minus ln p of x omega 2 minus ln p of omega 2. Okay. Now just take the ratio of these two, because these two are in logarithmic form and these two terms are in the difference form. So that means these two terms can be combined in this term, so that ln likelihood of class 1 divided by likelihood of class 2 samples. Okay, so we can write like this, and the posterior term can be combined together. So we will get this discriminant function in case of minimum error rate classifier, where we have seen that logarithmic function, which is a monotonically function, can help us to simplify the expression. So this expression is basically our decision boundary, if we will equate it to 0. So just let us consider a case that where the prior probabilities of these two classes are same. So if it will be same, then this term will vanish, it will be 0. Okay, then we have this term, and we have seen that this is nothing but the logarithmic of likelihood ratio, and this likelihood ratio is defined earlier, which can help us to make the decision if this likelihood ratio is greater than some threshold, then we can define that as class 1, and if it is less than some threshold, then we will define as class 2. Now let us discuss the Gaussian density function. It is also called the normal density function. In our real life, most of the events, most of the experiments outcomes are following the Gaussian density function. Like our speech signals, like if we consider the MNIST data set, so their noise are generated. The noise are the data set are contaminated with the noise, and those noise follow the Gaussian distribution. So very important to study this kind of distribution. So here we will study the univariate density function. So univariate normal density function having the two parameter, one is mean and another is variance. Okay, where sigma is standard deviation. So there are many advantages of this univariate Gaussian density function. It is analytically tractable, and also it is continuous density function. So in real process, we are dealing with the continuous variable, and there we can use this kind of distribution function because this is the continuous distribution function. And also in real life experiment, the events are basically asymptotically Gaussian. That means it follows the Gaussian distribution, and the value of the event will be 0 when we approach to infinity. That means if we have the Gaussian distribution of any experiment, if the outcome of an experiment follows the Gaussian distribution, then it has something like this, where on x-axis this is the event and on y-axis is the probability density. So here the probability of occurrence of the event at this position is not equal to 0. It will be 0 at the infinity. That is the meaning of asymptotically Gaussian. So that is why this distribution is very important for many real life experiments. So as I discussed, this is very important in handwritten characters. Our speech signal follows the Gaussian distribution. Even our random process contains the noise that also follows the Gaussian distribution. So mathematically, the Gaussian distribution is written as using this expression. So Px equal to 1 by root over 2 pi into sigma. So here sigma is nothing but the standard deviation into exponential of minus 1 by 2 x minus mean divided by standard deviation whole square. So here mu is the expected value of the experiment. Okay, and sigma square is the expected variance of the experiment. That means how much variations are in the data. Here the variance tell us that how much variation, how much spread in the data that can be given by the variance. Now let us try to understand using this plot. So suppose we have a univariate normal distribution and it has mean value mu and standard deviation sigma square. Then we will have the maximum probability density at mean, and that value will be 1 by root over 2 pi sigma, because what is the expression we have? Px equal to 1 by root over 2 pi sigma exponential minus 1 by 2 x minus mu divided by sigma square. Okay, so in this expression just put x equal to mu, then this term will be 0 and then the exponential of 0 will be 1. So this is our maximum value that we will obtain at our mean. Then the importance of the standard deviation is that our central limit theorem or control limit theorem says that if we consider the range on this x-axis, that if we have considered the range from mu minus sigma to mu plus sigma, then 65% of the data generated by using this experiment will be in this range. Okay, that means this is the spread of the data that can be defined as by the variance or standard deviation. So here, whatever the experiment we are performing, and the most of the outcomes will be in this range, and that outcome is basically the 65% of the data will lies in this range from mu minus sigma to mu plus sigma. So we will have 65% of data in this range. And if we consider this range, that is mu minus 2 sigma to mu plus 2 sigma, then here we will obtain we will see that the 95% of the data lies in this range. And if we consider the 3 sigma, it will be 99.7% of the data, it will lies in this range. So here this is called 2 sigma limit, this is called 3 sigma limit. In many statistical processes, these two limits are very important, that we observe that in many processes we control by considering these limits. Okay, so this was the univariate normal density function, which is defined by the mean and variance. Okay, so univariate normal density function having the one-dimensional variable, but we can have the d-dimensional variable as well. So if we have defined x in d-dimensional space, then we can define our multivariate normal density function as the mean and covariance. So instead of variance, we will have the covariance. The covariance is basically having the characteristic that in the diagonal, here covariance is basically the matrix, and this covariance tells us that how the two different dimensions are related to each other. That means by varying the one dimension, how we can observe the other dimension. What will be the effect on the other dimension? That means it tells about the dependency between the two variables in the d-dimensional space. So we will come to this, we will solve one problem, then it will be more clear to you. Okay, so this normal density function is defined as Px equal to 1 by 2 pi the power d by 2, where d is the dimensionality of the data, and the determinant of covariance matrix power half into exponential minus 1 by 2 x minus mu transpose into covariance inverse into x minus mu. So here we have x as a feature vector because it is not a scalar quantity anymore. This is d-dimensional feature vector. So that is why we have written this one in the matrix form. So here x is a column vector. So if we will take the transpose, then it will become a row vector 1 cross d. Then we have to multiply with the inverse of covariance matrix, and that will have the dimension d cross d. And again we have to multiply x into mu, which is a column vector. So d cross 1. So when you will compute this internal term, then we will find the dimensionality of this computation will be 1:1, which is a scalar quantity. So that means this multivariate density function, it returns us a single value at a given position. That means it returns the density of a variable in the d-dimensional space. Okay, so here mu is the mean vector because it is not a scalar quantity anymore. So here we are dealing with the d-dimensional feature space, so we will have the mean vector. Also we will have a d-dimensional mean vector, and then we will have the covariance matrix d cross d, and we can define the covariance matrix as one by n minus 1 summation x minus mu into x minus mu transpose, where we have to take the index I to 1 to n. So this is our covariance matrix. So here the covariance matrix having the dimension of d cross d. So if you will check the inner term inside the summation term, so xi minus mu, so this will be a column vector of d cross 1, and we are multiplying with the transpose of this vector, then it will be 1 cross d, and the resulting matrix, it will give the d cross d. So we have to take the summation of the d cross d matrices for each individual feature samples or data sample, and then we'll take the average. Okay, so this is our covariance matrix. And if we will see the covariance matrix, how the elements, what is the significance of the elements of the covariance matrix, we can write sigma 1 square, sigma 2 square, and sigma d square, and it will be some row 1 2 sigma 1 sigma 2. Okay, similarly this will be same sigma 1 sigma 2, sorry, row 1 into sigma 1 into sigma 2. So similarly, we can have the other terms. So here, the diagonal terms of the covariance matrix is the variance of individual components or individual axes in the feature space. So this diagonal element, like one of the example you can consider, sigma 1 square is the variance of the feature component x1 in the d-dimensional feature space. See, similarly, other diagonal element. And if we see the off-diagonal element, then this rho is the correlation coefficient, and sigma 1 and sigma 2 are the standard deviation of first feature component, and the sigma 2 is the standard deviation of second feature component. So this is the covariance, that how the two feature components are varying with respect to each other. Clear? Now let us see that how the multivariate density function looks. So try to understand this multivariate density function with respect to some experiment. And suppose we are in the two-dimensional space where the two feature components are x1 and x2. So if we consider the two-dimensional feature space, then our multivariate density function will be Px equal to 1 by root over 2 pi power d by 2. So here we have to determinant of sigma 1 by 2 exponential minus 1 by 2 x minus mu transpose sigma inverse x minus mu. Okay, so here d equal to 2. So we will obtain the probability density function for two-dimensional space, that means two-dimensional Gaussian density function. So it will be 2 pi 1 by 2 into exponential minus 1 by 2 x minus mu transpose sigma inverse x minus mu. So here the dimensionality of the sigma will be 2 cross 2, because we have seen that the covariance having the dimensionality d cross d if we are dealing with the d-dimensional Gaussian distribution. So here we are trying to write the Gaussian distribution for the two-dimensional space. So we'll have the covariance of dimension 2 cross 2. So these black dots are basically generated using the Gaussian distribution following this equation, where it has some mean value. Suppose this is x0, x10, and x20. So mu is x10 and this is x20. Okay, and the covariance can be calculated, or maybe it will be given to us. Okay, so these black dots are generated using this two-dimensional Gaussian distribution. Now suppose we want to compute the distance of a point from this distribution. We want to compute the distance of this point from this distribution. So what is this distance? How we can compute it? So before this, let us discuss the Euclidean distance. So suppose we want to compute the distance between the 2 points where the coordinates are x1, y1, x2, y2. Then we will have the distance equal to square root of x1 minus x2 square plus y1 minus y2 square. So this is our Euclidean distance. And if we write the expression for d-dimensional feature space, then the distance, Euclidean distance, will be summation over xi minus yi square, where I from 1 to d and power 1 by 2. Okay. But when we will calculate the distance of a point from this distribution, can we use the Euclidean distance? No, because the Euclidean distance is defined for the distance between the 2 points. But here we are trying to compute the distance of a point from a distribution. So in that case, a Mahalanobis distance is defined, which is given by r square equal to, I'm writing in the matrix form, so x minus mu transpose sigma inverse x minus mu. So this is basically the Mahalanobis distance, the distance of a point which is x point. So distance of point x from this distribution, where mu is the mean of the distribution and sigma is the covariance of this distribution. And this distribution is basically the normal distribution, and which is given by n mu covariance, because it is d-dimensional Gaussian distribution. Okay. So here we have the two different distance. Can we find any relation between these two distance? What is the condition in which these two distance will be equivalent? If the covariance is a identity matrix, if the covariance is the identity matrix, that means the distribution will be circular. Then this Mahalanobis distance will be equivalent to the Euclidean distance, where we will compute the Euclidean distance from a point. We will compute the Euclidean distance between a point and the center of the distribution. That means the variance will not the part to compute the distance. So now let us prove this, that Mahalanobis distance will be equivalent to Euclidean distance when the covariance will be identity matrix. So Mahalanobis distance so here we are taking the square distance. So Mahalanobis square distance is given by r square equal to x minus mu transpose sigma inverse into x minus mu. So where mu is the mean vector, that means mean of the distribution, and sigma is the covariance of distribution. Okay. And I told you that if the covariance will be the identity matrix, then it will give you the the Euclidean distance between the point and the center of the distribution. So if the covariance is identity matrix, then that means the inverse of this will be also identity matrix, and then just put here, then R square will be x minus mu transpose I into x minus mu equal to, then here identity matrix we can remove it, because after multiplication we will get this expression. Okay, and this is equivalent to x1 minus mu1 square plus x minus x1 minus x2 minus mu2 square plus x d minus mu d square. So here, if we compute the distance, Euclidean distance, then it will be x1 minus mu1 square plus x2 minus mu2 square plus x d minus mu d square. And we can write this one as a summation term. So it will be xi is basically the component of the feature vector x minus mu I, where I equal to one to d-dimensional space, so square, and whole term will be minus 1 by 2. So this is our Euclidean distance. Okay, so this is the